This is lab 3 covering black holes for physics 2211. So in this lab, we're going to be modeling the motion of a star that's orbiting a black hole with an unknown mass, and by using the change in position, we're going to find the F net of that star, and then in order to find the black hole's mass. And the F net in this case is strictly just going to be the gravitational force of the black hole on our star. And then in order to do all of this, we're going to be using Newton's second law of motion in addition to his universal law of gravitation. So in order to find the F-net discussed in the last slide, we are utilizing our known mass of the star, which is 2 e to the 30 kilograms, and our gravitational constant of 6.7 e to the negative 11 over the span of one day in our first formula, which is our universal law of gravitation, and by setting it equal to our change in momentum, with that being our only force acting on our system. Alongside this, we are going to chart the perpendicular and parallel forces that make up our F-net as the star orbits the black hole using these other given formulas. In the given code, I first start out by initializing our constants for our g and our star dot m using the variables known in the previous slide. With this, I also set my Georgia Tech email as the seed variable in order to generate a unique trajectory for our specific star. Following this, I use the momentum principle and Newton's second law to first calculate our momentum vectors using the generated velocity vectors times the mass of our star. Next, I found the change in momentum, which is simply the final momentum minus our initial momentum, and then found our dp dt using our delta t, which is essentially saying we're dividing by the change in time over that interval, and then immediately set it to our F net since it's the only force acting on our system. After, I then use these shown component formulas to find our perpendicular and parallel forces in our system that'll soon be modeled on our chart. And then finally, using our known information, calculated our star's mass using the gravitational law. Here we have the model that our code generated, now including arrows which are shown below that now model the associated component forces acting on our system as the orbit occurs, using an arrow scale of 5e to the negative 17. As you can see from the model, our star's perpendicular force is always perpendicular to the forward motion at any given point in the orbit, and combined to give our F net represented by the orange arrow. Additionally, notice how our arrows are shifting significantly as the distance between our system and the black hole either decreases and increases as a result of the law of gravitation. Additionally, using this model, we found our resulting mass of the black hole to be 1.57 e to the 34 kilograms. This model and the formulas used show how Newton's law of gravitation is comprised of our different variables of g, our two masses, and the distance between them, and show how it affects the forces acting on our system from the object that distance away. In our case, we utilize the fact that we can have our F net be strictly equal to our change in momentum. However, in a real world instance, there's likely going to be many other forces from other objects acting on our system, which would cause some changes to not only our F net, but the perpendicular and parallel forces that comprise it, and therefore our orbit and mass would not be as similar to the one that we've projected. Now, in an instance where the black hole were to suddenly disappear and immediately be replaced by another black hole of the same mass as the first one, because of our law of gravitation, we would have exactly no change in the force acting on our star orbiting it, since, as seen in the law, if you just replace the mass with another instantly, the formula remains the same, and the final result wouldn't change in any sort of way. Knowing that Newton's law of gravitation would always hold true, and in this scenario it remains the same.